All right, since we didn't have time to actually demo an implementation in class, I wanted to quickly run through an implementation of Fenwick trees so that you can see how easy they are to implement. I'm not going to go through in detail how Fenwick trees work, but just to remind you, this is a way of storing data so that we can perform range sum queries very efficiently. So we can store things across a in an array without using too much extra space, but it enables us to actually sum up subranges of the array very quickly. And we're going to use this least significant 1 bit, if you remember how that works, to kind of figure out which elements in the array contain the values that we care about. So each element in the array, instead of just storing the value for that one element, it stores the sum over some subrange. And if we figure out which pieces of those subranges we need, we can quickly sum up the numbers from 1 to n. So this is an example of a Fenwick tree. And then if we want to actually sum up the values from 1 to n, like we can basically do it by taking the individual bits and the numbers that they represent and kind of taking 1 bit off at a time to get the value that we want. So let's say that we wanted to sum up from 6 to 12. To do that, we'll sum from 1 to 12 and we'll take off from 1 to 5. So to sum from 1 to 12, we're going to need to take the value that's stored in 12, which that keeps the range from 9 to 12 in it, and then the value stored in 8, which has the range from 1 to 8. Okay, so we start off with 12 itself. That's the number we care about. And then the next number that we need, we're going to take off the value from there, and that's, oh, I skipped it, and that's going to give us the 1 to 8 from what's after that. As far as 5, we would have the number 5 and the value that's stored in 4, which is the numbers from 1 to 4. So adding those two values gives us the range from 1 to 5. And so when we subtract one from the other, we get 6 to 12, which is what we cared about. And on the other end, we can update the Fenwick tree by adding on the least significant bit, and that will give us the numbers that contain the element that we care about. So let's say that we want to update element 11. If you kind of look at the tree, 11 is contained in nodes 11, 12, and 16. Those are the three elements of the array that include within their range the number 11. So we would get that by taking 11 and adding on the least significant bit gives us 12. And again, adding the least significant bit gives us 16. And then we're done in this particular Fenwick tree. Okay, so I'm going to change over to show you some coding. So we'll run through a fairly quick example here, but I just want you to mainly see how easy it is to implement something like a Fenwick tree. So I'll start out with just setting up a basic C++ program. We're going to need to use a vector to store the data in the array itself. And I'll go ahead and set up a main command, even though we won't get to it for a minute. Okay, so in order to do this, we're going to create a data structure of class. So I will create a class, let's call it FT for Fenwick tree. And in this class, we're going to store a couple of things. One is going to be the size of the tree itself. So we'll have an integer n for that. The other thing we'll do is we'll store the values in the array. And remember, since these values are sums of numbers, it's helpful to have something that can have big values. So I'm going to make this a vector of long longs, and I'll call it v for value. Okay, and so now we need to create the commands that we want to be able to work with a Fenwick tree. So one thing we're going to need to do is instantiate it. So we need a constructor. So we'll just say Fenwick tree, and n is going to be the input. And remember, Fenwick trees are one indexed. So they go from 1 to n rather than from 0 to n minus 1. So if we want a Fenwick tree of size n, I shouldn't have used n there. Let's call it a. We were going to say n is going to be a plus 1. So we'll just make n the largest value in the array so that we could go up to it. And we are going to say v will get initialized to something then of size n, and we'll set all the values to 0 initially. So when we create a Fenwick tree, there's nothing in it. It's just all zeros at that point. Okay, so one of the things we want to be able to do is we want to sum up ranges. If you remember, we're going to need to get the least significant 1-bit. So I will create a routine to do that. So if we want the least significant 1-bit for X, we are just going to return X bitwise AND of minus X. And because of the two's complement form, when you do bitwise AND of those, it's going to give you the number that has the least significant 1-bit. Okay, so we've got a constructor. Now let's go ahead and do a range sum query. So if we want to sum up, this is going to sum up everything from 1 to A. If, in fact, let me go ahead and write this right now. If we want to sum up a range from A to B, okay, so we're going to go sum all the values in the range from A to B. We are going to do that by returning the range sum query of B minus the range sum query to A minus 1. So basically taking off everything less than A and up to B. So really the only thing we have to implement of any significance is the one that sums everything up to A. So here we will set up the total that we want and initialize it to 0. And remember, we're going to basically keep summing up values by taking A and then subtracting off the least significant 1-bit. So as long as A is greater than 0, until we basically run out of bits in the number that we care about. Let's fix that. Sorry about the typos. Okay, so as long as A is greater than 0, we will add whatever is in V sub A to our total. And we will say A is going to subtract off the least significant 1 for A. So we just take that off and finally return the total. Okay, and that's pretty much it. That's going to sum up ranges over the Fenwick tree. So that'll get the sum from 1 to A. Again, we just are subtracting off 1 bit at a time, and those are going to be the elements of the array that contain the ranges we care about. So the other thing we need to be able to do is we need to be able to update. So we will have a command to update our Fenwick tree, and I'm going to update element A, and I'm going to change it by the amount X. And so keep in mind here that, just as a note, X is the amount element A gets changed by. Okay, so it's how much we change the thing that should be in index element A. All right, and so this is kind of, it's very much like the range sum query, except instead of kind of subtracting off the least significant bit, we're going to keep adding on the least significant bit. So basically, as long as A is less than or equal to N, or actually we set N to N minus, or the size -1. So we can't actually go to up to N. That's why I believe I set it to, yeah, I set it to the size +1 up here. So that's the maximum that we want to go to. So while A is less than N, we will say V sub A plus equals X. So we're going to just update V by X. And now we will add on the least significant 1 for A. And yeah, that's it. That's all we have to do there. Okay, so that's how we update our Fenwick tree. And now we're done. That's all we had to do to create a Fenwick tree. So we have code there. It's not very long at all. It didn't take very long to write. So we've created a Fenwick tree. So let me just go out and make sure. Nope, I have an error in there. It's line 23. There we go. So had a typo in there. So with that typo fixed, let's just make sure there's nothing else. Okay. So let's go ahead and see how we could set this up. So we'll just do a really simple example here. I'm going to have N, A, and B. So I'm going to first of all read in the size of the Fenwick tree that I want. And I will set up a Fenwick tree, call it Fen tree of size n. Okay, so we read in n and we create a Fenwick tree of size n. And then I'm going to read in values that I want to change. So basically this is going to be our update command. I'm going to set values in the Fenwick tree for a while. And I guess I'll say while a does not equal 0. Okay, so as long as a is not 0, remember everything's one indexed. If that's the case, I will do fentree.update a b. So I'm going to increase element a by whatever the amount b is. And again, read in a and b. Okay, and then once that's over with, then I guess I will go ahead and do queries. So I'll just do those forever. And again, I will read in a and b. And I will then say, the sum from a to typing today to b is then tree range sum query from a to b. Okay, so we'll just kind of keep outputting sums over whatever we care about. So let's test this out. And go ahead and run this. So first of all, I'll create a Fenwick tree. Let's just say it's size 10. And now the way I had it set up was I'm just going to enter pairs. So I'll say 1. I'm going to have the value 3. I should have put those on the same line, but it doesn't matter. 2 will get the value 3. 3 will get the value 4. 4 will get the value 1. 5 can get the value 2. 6 will get the value 3. 7 will get the value 8. 8 will get the value 1. Okay, so there's a whole bunch of, just values that I do there, and go ahead and set everything to 0 after that. And so now, if I want to sum a range, let's say I want the elements 1 through 3. So I want to get 1 to 3. And it says that the sum from 1 to 3 is 10. And if you look at how we set it, the values were 3, 3, and 4. And indeed, that worked. It was 10. Let's say that we wanted the sum from 4 to 6. Okay, 4 to 6 is 6. So if you look, 4 was 1, 5 was 2, 6 was 3. So 1 plus 2 plus 3 is indeed 6. If we wanted to, do the values from 3 to 8, we can do a range sum query that comes out to 19, which hopefully that's right. If we do value for 3 is 4, plus 1 is 5, plus 2 is 7, plus 3 is 10, plus 8 is 18, plus 1 is 19. So that's correct. From 3 to 8 is 19. So that just shows how this works. And pretty much it's pretty straightforward to implement this. The code is not complicated. It shouldn't take you too long to write your own Fenwick tree code. And then you can perform these range sum queries really quickly after that. So hopefully that's helpful in seeing just how easy these are to implement and use. And you can use them on your assignments from here on out.